to be a little bit different. There we go. So Mike's got it going. All right,
Awesome.
so we're going
Thank
to
you,
go ahead and
gentlemen.
start the class off again, multimeter basics. So we're just going to run through the fundamentals of our multimeter. And yeah, come on over here. And again, my name is Damon Bennett, so I'll just run you on through this multimeter training class. And we're going to start off by taking a look at our different meters that we have. You could have a couple of types of different meters out there. Your traditional meter, biggest problem that you run in with a traditional meter is it does not have an amp clamp. And for what we're doing out there in the beverage industry, the amp clamp is going to come in very handy. One of the reasons we're running the class is, like we had discussed before, a lot of people know how to use the meter to test voltage, but they don't know how to use the meter for other functions such as amperage, ohms, continuity. We're going to walk through all those settings for you. Now, you will find that some more higher end meters might have different functions on them. Microfarads, temperature, things like that. We won't get into that today, but if we go into a refrigeration class, we can go into more detail of all the different settings you might have on a more advanced meter. But we're just going to look at our basic meter for today. So to start off with, we're just going to go through a little walkthrough of what we're going to be doing. So we had our introduction. We're going to walk through electrical terms and concepts just so everybody's on board and we understand exactly what we're going to be talking about today. From that point, we're going to go into how to use the multimeter. Not only how to use it, but what you would be using it for and why you would be using it to test something. Go through some of the common multimeter applications and then open it up for any questions that you may have for the class. So to start off with our terminology, dealing with AC and DC, you definitely want to make sure that you've got a meter that's going to read both AC and DC. A lot of them are going to read AC, may not have the DC functions, and you're going to find out that with the equipment that we work on, we're going to run into a lot of DC components. We're going to have computer boards, batteries that are on the system, solenoids, other components that may run off DC. So you definitely want to make sure you have that. Biggest thing that you want to understand there is what is the difference between AC and DC. You've got alternating current for AC, direct current. Alternating current basically allows the electricity to flow in both directions. Direct current flows in one direction. So basically hot flows one direction, the return flows another direction. But with AC, it's sort of cycling back and forth. So you want to double check all your components when you're looking at that. Do you have an AC component? Do you have a DC component? Because if you hook up a DC component to an AC component, it's not going to work and may actually damage that component. Another thing that we have for terminology is the word hot. You hear a lot of people say the hot line, the hot wire. Hot is going to be your power. That is where your actual power is coming down the line, coming to your components. You're also going to have a neutral. Neutral is the return for that hot. So the hot line is running to the component, runs through the component. The neutral returns that to make a complete pathway. Without that neutral, the hot isn't going to actually run anything inside those components. So you need to have that neutral return. You're also going to have a ground wire. Normally, it's going to be a green wire. It can be other colors, so just be careful about that. I always say that ground wire or any wire that's out there is going to be the color of the last, whatever the last technician had on their truck. So you got to be a little careful of that sometimes. But it normally is going to be represented with a green wire. Ground is just there for safety. Electricity runs down the path of least resistance. A wire has almost no resistance. And what will happen is if you have a short, then from that point, your electricity is going to flow to your ground and possibly kick the breaker out, but at least prevent you from getting shocked. And that's what a ground wire is there, is just preventing electrical shock. You have the term voltage. And I always try to use just one single word to help everybody remember. And when you look at voltage, I think of force. Voltage is the measurement of force pushing the electricity down the line. A lot of people think that voltage is the electricity, but it's not. It's actually the pressure or force that's driving that electricity. Amperage. Now, amperage is what's going to actually be that electricity running down the line. So I always use the term flow. So it's a unit of measurement of electricity flowing down your conductor or down your wire. You have ohms and resistance. Just basically, I always hate using the same word to describe it, but ohms or resistance is just the resistance to that flow of electricity. So something preventing that electricity from flowing down the line. Now, I always say, think about electricity like water because electricity flows like water pretty much. You're going to have pressure to force that electricity down the line to flow to your components, just like water has pressure pushing the water down the line. You can have resistance, sort of like when you take a hose and you kink it on over, and now you don't have the water coming on out. Now, you can't kink a wire, but you can have some other things in there that cause problems with your resistance. Could be the length of your wire, the diameter of your wire, a loose connection on your wire. Those things can cause resistance, and as you have resistance, you're going to see that your voltage is going to drop. So you want to make sure that you have very little resistance in there, and it could be as simple as just a loose wire. And then you have continuity. Continuity is just a measurement between two paths, right? You're going to have 2 points, point A and point B. We want electricity to get from point A to point B. Does it have good continuity? Is something preventing it from getting there? It could be a switch turned off. It could be a broken wire. But all you're really looking at is, do you have a good pathway? And that's what continuity is. All right. Yep. Back up here real quick. So the next thing we're going to do is let's take a look at our meter. So we're going to take a look at a basic meter. And this basic meter, it's going to have all the component or all the functions that we need to be able to go out and do most common beverage equipment repairs. But we'll just go over the meter and how it actually works. And we'll start off with just the make of the parts within the meter. So you're going to have your digital display. This is going to be where everything reads when the meter is in the on position. So all your functions will read on that display. Right down here are the ports where your probes are going to go ahead and plug into. And this way you can go ahead and get voltage readings or ohms or continuity readings basically off. That does not like to stay up there. Every time I move that one wants to release. But you can go ahead and take your probes, put them onto your component or whatever you're reading, and go ahead and get a voltage, ohms, or continuity reading off of these ports. I'm going to have to buy another model of these. Does not like to hang on there. Other things that we have over here is you're going to have your dial. The dial is going to allow you to adjust what settings that you're going to put onto your meter, including the off position. There is an off position for the meters. Now, you may have a meter that's a little bit higher end, and basically as soon as you use it, it automatically turns on. Some meters you don't even have to adjust settings. I've seen some out there that you could just hook up and it will automatically detect what setting you need, and it goes ahead and does it. But most of them, I'd say 99% of the meters out there are going to have some kind of a dial on them, and you're going to have to go ahead and adjust your settings to what you want to read. But the key thing is just remember, you've got to adjust it to each setting. You can't leave it in the off position, have it automatically come on in. Another thing with the off position that works great is that if it does have it does shut down because it's been on for too long, just turn it off. Let it sit for a couple seconds, turn it back on, and it normally resets. It's not that your battery has died, it just needs to be reset and turned off for a second. But that is your dial. Come on over here, and you have got your amp tester, and this is where your amp clamp, basically I always call it an amp clamp, and it's going to clamp around a single wire to go ahead and give you an amperage reading. You have got your amp clamp lever right here, which will allow you to open this clamp so you can put it around a wire. And then this meter has got if I can keep from dropping it over and over again. This meter has got a couple of extra functions, but I do see that most meters have these somewhere. The key is going to be take a look at the manual for your meter to find out exactly how to make these work. But you should have a button someplace. One of them will be a data hold button, and the data hold button is used so that if you're maybe in a dark location and can't read the screen, maybe you've got this over your head, or you need that recording, but you don't have a piece of paper to write it down, you can hit the data hold button and it locks whatever is reading on the screen there so that you can look at it later. It just doesn't disappear. So that can come in pretty handy sometimes. There's also another button right over here on this left-hand side. Let me go ahead. Zoom in here. Maybe. Why is it that there we go. It's like now all of a sudden it doesn't want to zoom in. Right over here, there's a little button on the side. And that button is going to be your peak hold button. And that peak hold button is actually going to be used to lock in the highest reading that you have. And this one on this meter is designed for amperage. So if you're trying to get an amp draw and you need to know exactly how high your amps are climbing, you can go ahead and hit that peak hold button. And then as the amps go up and then drop back down, your highest reading will be locked onto your screen. So those are some of the functions that we have are on this meter, and they're going to be the basic functions that you find on almost pretty much every meter out there. It just might be that you have the buttons in different locations, different spots. Take a look at this one right over here, and you're going to see that all those buttons that we were talking about earlier, I've got some of those buttons right over here on this side. So again, according to what type of meter you have, could be a little bit different. So let's go ahead and I'm going to have a little interaction with you all. Let's go ahead and start off with a little knowledge test of what we just went on over. So if we were looking at the digital display, which number represents our digital display?
6.
All right, there we go. So number 6, digital display. How about our dial to make our adjustments?
Jeremy says 1.
Jeremy says 1, and answer is 1. All right, Jeremy. Okay, how about our peak hold button?
I'll jump in number 3.
There you go. Number 3, off to that side there. Number 3. So how about our amp clamp release lever?
That will be 4.
There you go. Number 4. That opens that clamp up so we can wrap that around a wire, get our amperage draw. How about our probe connection, where we plug our probes into?
Number 7.
There we go. All right. Our amp tester or amp clamp.
Number 2.
That's 2.
Sorry.
There we go. And the last one, our data hold button.
5. That'd be
There
5.
we go. Well,
Yeah.
yeah,
So
There you go.
I have one question. So on my multimeter, it's a Cobalt, just a digital, no amp clamp. I don't know if you could see it. Well, it has a 10 amp setting for the probe inlet on one of the sides of the commons. And it says for 30 seconds max every 15-minute fused.
yes. You know,
What
I've
would that
got
be?
one. I think it's almost the exact same one. You got that over at Lowe's, I'm going to guess. I got mine over at Lowe's.
Mhm.
And I was using it in this class. The problem that I had is that it kept blowing the fuse.
So yeah, what does that mean exactly?
It
Is that
means
just
that
go up to 10
you can
amps?
actually get, let me, you can actually get a reading with your an amp draw reading with your meter by using
Mm,
this style meter. But what you would do is you would basically take your leads, you'd
hmm
hook it up to the wire that was going to come to, say, a solenoid or a motor, and then you take
Okay.
your other lead and hook it to the motor. And basically, your wire is running through your lead, through your meter, back through your lead, and then going to the motor.
Okay, to
And
see
you're
how
getting
much the
the amp,
motor's drawing.
yeah, and you're getting the amp draw reading of how much that motor's drawing. The problem
Okay.
I run into is I was trying to use it on motors, and
hmm
the motor seems to have a little bit of a spike, sometimes dropping or jumping up to like 18 to 20 amps. And I was only staying there for a second, but that was enough to blow the fuse out.
Okay. That
So
makes sense.
that's one of the reasons that I actually like the amp clamp rather than that pass-through meter. It makes it a lot easier to be able to, you don't have to disconnect wires to be able to get your readings. You don't have to worry about blowing the fuse, but it can be used, especially when you're dealing with something smaller, like maybe a solenoid. Yeah, you definitely can use that for getting your amp draw readings. It just has to pass through the meter, into the probe, through the meter, out the probe to whatever you're testing.
Whereas was that on a carbonator motor? Because I know those are
Yes.
like 6.5 amps. So
Yeah,
they'll
that's
spike
that's
up to 18.
yeah. If you see it, they'll have. If you remember how I said I have the peak hold, I was
Hmm.
running the peak hold just to see, and they'll have a spike sometimes all the way up to 18. Not long enough to be able to trip a breaker, but
Hmm.
it's enough to trip a fast blow fuse or
Right, right.
to blow out
Okay.
a fast blow fuse. Now, if you had like a
Hmm.
slow blow fuse in the meter, that might be a little bit different, but that's not what my meter came with. It had a fast blow in
Hmm.
it.
Yeah, it says, I guess 30 seconds max.
Yeah.
So
I don't think mine
that
was
might
even
hold up.
that.
Yeah. Awesome. Thank you, Damon. That's a great answer. No, I
All right.
understand that a little better.
So let's take a look at, come on in. Next thing we're going to do is we're going to take a look at our multimeter settings. So for our multimeter settings, what we want to do, yeah, maybe. There we go. What we want to do is come on in and take a look at all the settings that are up on our dial and basically what those settings stand for, and again, what we're going to use them for. Now, one of the things that I see that people have the biggest mistake with is that you'll see that they have letters and they have symbols. So you got like an A with a wavy line, and then you maybe have an A with a line and a dotted line over top of it. And a lot of people don't understand what those stand for. So we're going to go on through and talk about that really quick. The key is just to remember the A is going to stand for amperage. And then when you see the letter V, that's going to stand for voltage. And then the symbols are what's going to stand for AC and DC. Wavy line being AC, the line and the dotted line being DC. And I see a lot of people make the mistake of thinking that the A stands for AC. And that, again, just remember, A stands for amps, V stands for volts. The symbol is what's going to tell you whether it's AC or DC. So let's go ahead and take a look at our symbols. And to start off with, you've got your AC symbol, A for amperage, the symbol of AC on the top, that little wavy line. Remember, we said AC flows in both directions. It can go forward, it can go backwards. That's basically what that little symbol is standing for. And the AC amperage is what you're going to be able to use to read the amount of electricity that is flowing through a circuit. It's telling you, is your motor or solenoid or whatever you're testing actually operating properly? Because is it drawing the right amount of amps? If it's drawing too much, it's working too hard. If it's drawing too little, it's not working hard enough. Sometimes that might be a very simple fix. Sometimes you may have to dig into it quite a bit, but it's going to help you understand, is it actually running properly, drawing the proper amperage? And again, that's for your AC. Next one that we have is going to be our DC amps. This is going to have A again for our amperage and the line and dotted line for our DC. And DC only flows in one direction. Hot flows one direction, the return flows the opposite direction, but it does not flow both directions like AC does. So a little bit different way of delivering electricity. And again, you got to make sure you're hooking up the components correctly. You don't want to hook an AC component to DC voltage or vice versa. I had a technician in a class one time give me a good example, and I thought it was really good, so I always share it. And he says, when you look at the DC symbol, it looks like half of a road, right? You've got the line on one side and the dotted line that's dividing the road. And he says you can only drive one direction in that lane. So that's the way that he always remembered it. And I thought, well, that's a good way to remember it. So just remember, DC flows one direction and you've got one lane to drive in there. So that's basically your DC amperage. DC amperage is going to give you the same thing as AC amperage. You're going to see how much electricity is actually flowing through your component, how well your component is using it. Make sure that you are within that 10% variable of where that should be. And you normally are going to find that on the data tag of your equipment, whether it be a motor, a solenoid, whatever that you're testing, should tell you what your amp draw should be. Next one that we have is going to be our AC voltage. And again, V standing for voltage, the wavy line standing for AC. And this is going to allow us to know, do we have the proper voltage being delivered to our equipment? That proper force, forcing the electricity down to that component. This is something you want to be within 10% of as well. If it's outside that 10% variable, you're going to find that it's not going to operate properly, may not be functioning right, may be overheating. So you want to make sure that your voltage is correct. And I always like to start right at the source, start at the wall, then go into your equipment, then start testing each individual component. But this is a really great place to start. So you just make sure that you're using your AC voltage if you're testing maybe your line voltage coming off the wall, or again, your AC components that are inside this system. You've also got DC voltage test, V for voltage, the line and dotted line for DC. And again, you're going to be able to test each one of those DC components to make sure that they have the proper voltage within 10% variable, plus or minus, just to make sure that you are getting the proper electricity. The last thing you want to do is start jumping in and working on the equipment and replacing parts to find out that it was something simple as I didn't have the correct voltage, and that was what was throwing everything off. So great test that you can go ahead and run there. Other things that you may have on your meter is going to be ohms, which is going to be like an omega symbol or a horseshoe. And that is what is going to be able to give you a reading of resistance. What's going to be the opposition pushing back on that flow of electricity. So you've got that force of voltage pushing forward, that resistance is basically blocking the line and it's not allowing that voltage to flow through. And what you might find is at the wall, you've got 120 volts, and at your component, you've got 85 volts. Well, somewhere you've got resistance in there. And if you did a resistance check, it's probably going to show up that, hey, you don't have a good flow. You've got some kind of resistance taking place. But another thing you can do is you can test the resistance in your motor or solenoid or whatever else that you're looking at, because everything that utilizes that electricity is going to have resistance inside of it. If it was zero, it would cause a direct short between hot and neutral, and it would just blow the breaker. So you'll find that pretty much everything using that electricity like a motor is going to have some resistance to it. Now, unfortunately, what you're going to find out is that on the data plate, it's not going to tell you what your resistance should be. So I always tell everybody, compare it to a good part. If you've got a solenoid and you've got 8 solenoids on a machine, then if you got a working one, test it and then compare it to the one that's not working and see are they properly or approximately the same amount. And that'll give you an idea. But really good test there. Next one we have is continuity. And I will say continuity and ohms are almost exactly the same, except for the fact there are 2 key differences. One, continuity will give you an audible sound when you're making a connection. So you hear a beeping sound the entire time. A lot of people like to use continuity because they like to see it visually on the screen, but they also get it audible with that beeping sound. The other difference is going to be continuity only reads up to 50 ohms. Your meter may go up to like 40 million ohms on the ohm setting, but on continuity it only reads 50. So when you're using continuity, use it for something that isn't going to have a lot of resistance. If you do, what you might find is you're going to have a big mistake because the meter is going to lie to you and tell you there's no continuity. You think there's something wrong with the windings or something wrong with the wiring, and it ends up being that it just was over 50 ohms and you couldn't read it. So continuity is always for reading something very, very small on its resistance. And we'll talk about that a little bit more here later. But that's your continuity, is just this audible symbol. So I'm going to have you guys go ahead and do a little knowledge check again. And we'll start off with which number is our continuity setting?
Number 6.
There you go. Number 6, that little audible symbol. How about our amperage or amps AC symbol?
1.
There you go. The A with the wavy line. A for amps, wavy line for AC. How about voltage AC?
3.
There you go. Number 3, V for voltage, wavy line for AC. How about voltage DC?
Number 4.
There we are. So number 4, V for voltage, line and dotted line for DC. How about our amperage DC?
2.
There you go. And last one is our ohm setting.
Number 5.
All right. Great job, everybody. Not for sure how well everybody was with knowing the symbols to begin with, but you definitely know them now.
I didn't hear Kevin answer a single one, so he
Well,
might be
we don't know
lost.
about Kevin then, do we?
I'm keeping my eyes on the road here.
No, be safe, brother.
Yeah, he'll answer during the watching of the video.
Yeah.
All
There
right.
you go.
All right, next thing we're going to do is we're going to go into the use of the multimeter. But before we do that, the first thing that I always like to talk about is safety first. You want to make sure that you are safe when you're using the meter. You're going to be working in an electrical area which may have high voltage. You might be working on 120 volts. You might be working on 220. I don't think we're going to be working on anything in the beverage industry over 220. But if you ever work in another area outside of beverage, you might run into something like 440 or 600 volts. If you are working on some old pieces of equipment with fluorescent light bulbs, there were some old equipment that we used to work on, which I believe the ballast actually boosted it up to 1200 volts. So something to be a little cautious about when you're working on everything. Make sure you're looking at the data plate, know what voltage you're working with. Also be careful when you're putting your hands into those electrical areas because you can get shocked. A lot of people don't realize this, but just so you know, 120 volts is actually more deadly than 220 volts. I don't know if everybody knew that or not. Main reason for it is, remember I said voltage is force. Higher the voltage, the more force it has, it normally will push you away, unless you're in an area that you can't get away from it. And I've heard those stories before. But for the most part, it will push you away. And I know that for a fact from one of the first jobs that I had after getting out of school. Worked on a apartment complex that had like 400 units in it. And it was a hydronic system. They used 440 volt system to control the fan motors for each room and just ran it in series through all 400 rooms of this unit. And the guy I was working with said he turned the breaker off. I went and I cut the 400 volt wires, and the breaker was actually mislabeled by the electrician, so he turned the wrong breaker off and basically blew me across the hallway.
Wow.
I was in a closet. I came out of the closet. I stuck my head into the drywall of the hallway and then hit the ground and was basically knocked out. But it flat pushed me away and moved me probably about 4 to 5 feet backwards, just completely blew me backwards. 120 volts, on the other hand, it does not have the force to push you away, but it does have the ability to cause your muscles to contract. So basically, you've got that wire in your hand, your muscles contract, you're hanging on to it. I did run into one of those myself also. This was when I was a little kid. And basically, you're sitting there looking at the wire in your hand going, let go, and you can't do it because your brain doesn't activate. So it's one of the dangers that you're going to run into. So again, be very careful when you've got your hands in those electrical boxes. If you're going to do testing, you've got to do it live. If you're going to do repair, shut the power off and make your repairs. Don't try to repair it live. You're probably going to end up getting shocked. And when you get shocked, you're going to kick yourself because you're going, why did I do that? A lot of people think, oh, I can make that correction while it's live. No, you're going to get hurt. And it does hit you pretty good. All right, so we're going to move on from safety and take a look at each step with our meter. So first one that we're going to look at is continuity. So remember we said continuity, all we want to do is we want to make sure that we can get a reading or basically electrical flow from point A to point B. We're looking at an electrical pathway for our electricity to flow through. A couple readings that you're going to have when you're using your meter, you could have 0 and OFL or anything in between. A lot of people get these backwards. 0 actually means perfect continuity, a perfect electrical pathway. A lot of people think that 0 means that there's no way that electricity can flow. It's 0. It's actually opposite. 0 means it's a perfect electrical pathway, no resistance in that pathway at all. Perfect continuity. OL or OFL, according to what your meter reads. Some manufacturers have it listed OL, some have it OFL. We tried to come up with what it stands for. There's about 30 different terms of what it is. Nobody is consistent on what it is. I always say it's open line.
Yeah.
You can fill
Yeah,
it
I
up
agree.
with whatever
Yeah.
you want. But that normally stands for open line, meaning that there is no pathway, there's no way electricity can get from point A to point B. All right. OL or OFL normally means that you've got a disconnected wire, a broken wire, something has happened that's broken that pathway, maybe a winding inside of a component that's actually burned out, but it's preventing you from having that pathway at all. What you want to test with continuity. Remember, you said continuity has a max reading of 50 ohms. So you're testing things that are allowing electricity to flow, not utilizing electricity. So we don't want to test motors with continuity, but we will want to test things that are allowing electricity to flow, like wires, fuses, switches, things like that, where electricity flows through them. So let's take a look at, move these meters out of the way. Let's take a look at something that we can go ahead and test with continuity, which would be a fuse. There we go. My camera's backwards. All right, so we can go ahead and test a fuse and see, are we actually getting a pathway through that fuse? Now, a lot of people say, I can see through the fuse. I don't need to test it with a meter. Well, not all fuses are going to have glass case on them. Some fuses might be paper wrapped, so you can't actually see. Other times, the filament in the fuse is so small, you might not be able to see if it's there. I've also seen it wrapped around things. So using the meter is going to give you an exact reading of whether it is or is not able to pass electricity through that fuse. Now, for our meter, what did we want to go ahead and set our... Keep doing that. I've got these cameras.
Live TV is great.
Yes. What do we want to go ahead and set our dial to be able to read this?
The sideways Wi-Fi symbol.
Yeah, the little, it's like I always call it an audible symbol. But yeah, that little sideways, little microwave symbol, is that what you said?
I said it's sideways
Wi-Fi?
Wi-Fi.
Oh,
Sideways.
Yeah, like
Wi-Fi
at the
symbol.
bottom of your
Okay.
computer, it's like that, but
Yeah,
on its
yeah.
side.
Yeah, I'm old schow, right? I talk about Wi-Fi symbols. It's like hashtag. It's like I called that pound sign, but okay. I always like hashtag. It's like, what was pound too long? You had to change it to hashtag? What?
Yeah.
All right, so all we're going to do is we're going to take our meter. We've got it set on over to our continuity, and we're going to go ahead and read our fuse. Now, a couple things you want to do before you are actually trying to read your fuse, and that would be you could remove the fuse like I have right here, or you'd have to at least disconnect one wire terminal coming to the fuse, right? So you can leave the fuse in its fuse box if it had a wire coming in and a wire coming on out, but you have to disconnect at least one. Reason for it is we want to have a pathway from point A to point B. If you have your wires still connected, this may be broken, but maybe it goes down another wire, goes through the windings of a motor, and then comes back the other side and is giving you a false reading. So if you isolate it, basically disconnecting a wire from at least one side, that will allow you to be able to get a reading. The other thing is before you do continuity or ohms, you want to make sure that you power the system down. When you're doing continuity or ohms testing, you're using the 9-volt battery that's in this meter. And if you try to do it live with 120 volts on the circuit, it's going to end up possibly damaging your meter. Sometimes the meter has a fuse in it. You just replace the fuse, you're back up and going. Other times it does not, and it might have what's called a shunt. And a shunt is supposed to redirect the electricity, but I have found that shunts don't always work. This meter has a shunt, and I've had technicians that have this meter say that every once in a while they made the mistake and it blew the meter out and the board went bad. So not 100% safe on that. And the key is, if you're doing continuity or ohms testing, power down, isolate your circuit, and then go ahead and do your test. So from that point, we can come on over and we're going to get a reading across our fuse. And you're seeing that we are at what, 0.2? So pretty much right there at the zero. Like I said, continuity should have almost no resistance. So we can test out our fuse and see how that works.
Now, on your end, Damon, you had the audible tone. I know a lot of microphones mute that out.
Yeah, thanks, Mike. Yeah, you guys did not hear the audible tone. I think my microphone has noise canceling that cuts out some of that.
Right.
So
Yeah.
so it should be making a high-pitched beeping sound. Or maybe, did anybody else hear it? Maybe it's just Mike's ears. Maybe Mike can't hear that pitch anymore.
Well, that could
I
be
definitely
well.
can't.
No, I didn't hear it.
No, we
Like,
didn't hear it.
My kids brought me something the other day. It was a video that had said you lose this range at certain ages, and it kept changing the frequency. And it's like, man, I got to a point, and I'm all, are you honestly hearing things still? And they're all, yes.
Oh, wow.
But I can hear this one, but yeah, you probably can't hear it on your end. But on continuity, you can hear that audible beep. So you can go ahead and test out your fuse. Another thing that you can test with continuity is going to be simply a wire, right? You can have a long piece of wire. And on your wire, you just are going to come on over and take your meter, and you would read from point A to point B. And are you actually getting a reading?
May have heard a beep there for a second, but yeah.
I did hear a beep.
Yeah.
And I will say, you notice how it's jumping around. The tighter
Yeah.
that you hold your meter to what you're reading, the lower the reading is going to be. So if you're just lightly touching it up against something, you're probably not going to give a proper reading. And so you might be talking to somebody on the phone saying, yeah, I'm getting like 25 ohms on this. And they're, well, that's way too high. But it's because you're just lightly holding it. And then if you hold it really tight up against there, it's like, yeah, I'm down at 0.7. So it does make a difference. You have to hold it nice and tight when you're trying to get that reading. Now, other things that you can read could be switches. So we may have a couple different switches out there. You may have a toggle switch. Zoom on in here a little bit more. So you can end up having just a toggle switch over here, just on and off. You may end up having like a little micro switch down here. Some people call it a cherry switch, but cherry is just a manufacturer name, but it could be a micro switch. So you can go ahead and read things like that. So what I'm going to do, because I can't actually hold this and show it on the video at the same time, I'm going to go ahead and, well, unfortunately, I'm not going to do it with that set of cables.
Is that like a pincher attachment?
I've got some
Like
alligator clips.
Yeah, like an alligator clip.
The one cable I've got hooked up to my meter does not have threads on it for the alligator clips to go on. This one does. I was wondering why I had it on a set that wasn't connected. But we will go ahead and screw that on in, maybe.
That's a cool attachment.
Yeah.
This comes in
I was
really
just
handy
looking at mine.
for, when you need a third hand or something. Also, when you're working on compressors, you really need to have a really tight connection to be able to do a compressor, and you can't hold it tight enough. You'll see that your readings keep fluctuating. So I always go ahead and use the alligator clips when I'm doing a compressor. Then I'm going to come on over here. We will pop these on out.
While you're setting that up, I want to throw in never touch the leads with your hands, well, especially with voltage, but on continuity and ohms, you can get a false reading just, reading just the electricity traveling through your body.
Hmm.
So don't
Okay.
touch the leads.
Yeah, you're not going to get shocked off of it, but exactly like Mike said, you can get a false reading because right now I have OFL. If I touch the
Mhm.
leads together, remember I get perfect continuity, I'm going to get close down to zero. Well, 0.0 complete would be perfect. I'm at 0.1. Your meter's always going to be a little off. It normally says plus or minus 2 or something like that, according to how they are made. Let me go ahead and hit the alligator clip, see if it gets me to zero. No, it's still at 0.1, just a little bit of resistance. But like Mike said, if I went and I touched the leads and I had my fingers on it, well, let's move that into ohms. Is he going to lie to me, Mike?
Moisturize, moisturize your hands. No, no,
Yeah.
Yeah, my hands are too dry.
no. Maybe the alligator clips won't read it, but I know
There
the
we go.
probe
It's
will.
reading.
Yeah.
If you look at the meter, I'm getting a reading, and it's just because of the fact I'm touching it with my hands.
Yeah.
So if you were coming in here and working on this and you were touching your leads while you're actually trying to get a reading, you may not be reading the switch. You might be just reading through your body.
Yeah.
So just be careful with that. Good point, Mike. Thank you. So another thing that we can do, like our on-off switch, is we can just come on in and we can get a reading through this, and we're going to make sure, is it actually working? The key is it needs to do both things. It needs to turn on and it needs to turn off, right? So right now you'll notice on the meter, I'm getting a reading. That means that it should be in the on position. And then when I switch it to the off position, go ahead and stick it back on there. Stick it to the off position. Now we have got OFL. And then again, we flip it back to the on position.
Okay.
And we're getting a reading. So that's telling us that it is working properly. It's allowing electricity to flow, and then in the off position, it's not allowing that electricity. It's blocked that pathway, that continuity pathway. So that is telling us that we have got a good switch. Now, I always warn everybody, if your switch has high resistance, because you notice that we're pretty much close to zero, right? 0.10.
Mm-hmm.
But if I have high resistance, maybe I get up into a whole number, or maybe it's like 1.2 or 2 or 3. From that point, I'm looking at, I've got resistance building up inside my switch. One of the things you're going to find with resistance is resistance causes your amp draw to go up. It's causing that voltage to work harder to push through it. It's going to cause the amp draw to be harder. And what's going to happen is it's going to cause your switch to heat up. And if you've ever ran into any kind of a switching component that burned out, and then you replace the switching component, maybe even had to cut the wires and rewire it because the wires had burned, and then everything works fine. And it's like, why did that just burn out? More than likely because you had resistance with inside your switch. And you will see that most of these switches should be running close to zero. If you start to see a high reading, go ahead and replace it before it burns it out and shuts that customer down. So that's a good thing to look for when you're out there working on your equipment. Not just is it turning off and on, but does it have high resistance in it as well? All right, over here we have got our micro switch. And with our micro switch, you're going to have a common connection. You're going to have a normally open and a normally closed. So you could wire it where it's normally open, meaning that there's no power, until my little switch down here is activated. Or you could have it normally closed, where that means that you've always got power to it until the switch is activated, then it opens it. The key is, what is normal, right? Normal, when you're looking at open, just means that there's no pathway. When you're looking at closed, there is a pathway. So we're going to come on in.
And that's important when doing soda valves to make sure that you're putting it in the correct way.
Yes, absolutely. And man, I cannot read this to save my life. Pretty sure that is.
Oh, you're looking for the NO or the NC?
Yeah, they should be marked as NO, NC. There we go.
I'll have to make a graphic for that, Damon. Wrote in there.
Yeah, I think a graphic would be
Yeah.
better than to doing this live because I can't even see it marked on here. But there's like little symbols down here if you look really close. So basically, you're going to have a common. Common will always have a wire connected to it. Then you make your decision. Do I want to go NO or NC? So when you're dealing with a fountain valve, would that be a normally open wiring or a normally closed wiring?
Normally open.
There you go, normally open, right? There's no power until I press my switch. And then you see that I have got a reading on my meter, and then I release my switch and we go back to OFL. So it allows the electricity to flow through the switch when it's pressed, but it shuts off when it's not pressed. Or you could wire this the other way and we go normally closed, which means that I have always got power flowing through this switch until the button is pressed, and then that shuts the power off. So either way, this is the way that you're going to want to go ahead and test it. So you're just going to go ahead and run the meter connections the same way that it would be wired, making sure that as you press the button, it's actually opening and closing. And if it's doing that, your switch is doing what it should do. And I don't know if you guys noticed, but on this one had a little high reading to it. This might be something that I'd be looking at. Okay, this might be failing here pretty soon. But the key would be just compare it to another one. And if the other one is very low, say you got a new one or another one that's working properly and you got a very low reading, and then you test the one on, you've got test the one that's giving you a problem, you got a very high reading, then go ahead and replace it. All right, so that is our continuity. Any questions on continuity before we go ahead and move on?
I was going to mention, Damien, the testing of the fuse that you were showing.
Yes.
I've seen a lot of times techs will get that fuse out and they put it on the counter, and you know how some of the sites may have the stainless counters, and they would get a false reading when
That's
they
a good point. I wasn't thinking about that. Yeah, if you stuck it on the stainless steel counter, then it's just going to allow that to go right on through. It's going to make a connection through the stainless steel of the counter itself.
Right. So
Mhm.
that was just a point I wanted to bring up, because it does happen. Sometimes they're in a rush and they'll sit it on the counter, take the reading, and it's reading good, but then when they go to put it back in, it's not working.
Or even if you got a standard countertop, right? And it's wet because you've spilled some moisture on there, water or, a pop or whatever, then that water could cause that to actually come across as well. So that's a good point. Make sure that you're aware that nothing else would be influencing that electricity flow through that fuse. But
Yeah.
like Mike was saying, don't sit there and grab a hold of the fuse and hold your meter up to it and
Yeah.
hold it with your fingers, because then it goes through your body as well.
Correct.
All right. Good point. All right, so we're going to take a look at ohms. So ohms is almost exactly the same thing as continuity, except for the fact that continuity only went up to 50. So that's one of the big things that we'd be looking at. When you're dealing with ohms, you're really looking at, okay, we want to take a look at how much resistance our load has. A load is what is utilizing the electricity, like a motor that's taking that electricity and converting it on into mechanical energy, or a light bulb that's taking that electricity and converting it into light energy. We want to make sure that that load actually has the right resistance. Remember, we said every load is going to have resistance to it. It's not just allowing the electricity to flow through it, it's actually utilizing that electricity. So it will have resistance for that reason. So when you're checking a load, you may not know what resistance it should be, but two things that I always look at is it a zero reading? Zero reading means it is a direct short. That means that the electricity is flowing directly from the hot leg to the neutral leg, and it's not going through the winding at all. And that's going to cause it to be a direct short, more likely kick your breaker as soon as power is applied. Another thing to look at is it giving you a reading of OL or OFL? And in that case, you might have a bad or broken winding inside that motor or solenoid or whatever load that you're testing, filament in a light bulb. So that's going to tell you you have no continuity or no pathway through it. So those are two things to check really quick. If you want to get into it even more, you're not getting a zero, you're not getting OL, OFL, you are getting a reading, but it still doesn't work. You can compare it to a good part. And like I said, say it's a solenoid on a fountain machine. You might have 8 valves, right? 7 of them are working, 1 doesn't. Compare a good solenoid to what the reading is of the one that's not working and see, is it giving you a different reading? If so, go ahead and replace your solenoid. So that's a good one. Or maybe you have to go to your truck and test a motor. But that's probably the easiest way to go ahead and test to make sure that it has got the right reading to it. And as long as they're close, it's not always going to be exact, but as long as they're close, then it should be good. Another thing that you may want to do is test it for a short to ground. So disconnect your wiring so you have no electricity flowing through your component, and then go ahead and test it between your electrical leg and the frame of the machine or the frame of the part that you're testing. If you've got a reading between the electrical line and the frame, that's telling you you've got a short to ground, and that's going to have to be replaced as well. So if you get a 0, that's telling you there is no short to ground. If you get, if you get a 0, if you get a 0, it is a direct short to ground. I'm saying it backwards. If you get a 0, it's a direct short to ground. If you get OL or OFL, then it's telling you that you have no continuity or no short to ground. So to be able to give you an idea of that, let's go ahead and take a look at, say, a solenoid. So we've got a solenoid over here. First thing that we want to do is go on over and make sure that we are on ohms. And we're going to go ahead and get a reading on our solenoid. And it's basically going to tell us how much resistance does that solenoid have. And again, if we had a 0, it would be telling us we had a short. If we had OFL, it'd be telling us that we have no pathway through there. Our winding has probably got hot and burnt, and it's not allowing electricity to flow. If we have a good reading, again, compare it to another good one to see how that compares out to it. But that's a good reading right there. Another thing that you can do is do the same thing with a motor. So if you had a motor, you can do the same test. Now, I'm not going to unplug this, but normally you would come on in and unplug it and then go through and do your testing. What I'm going to do is I am going to come on over, and there are areas that you could put your wires and lock them in with a wire nut or with a nut. I'm just going to go ahead and test it right there. But you would normally come in, disconnect your power down, disconnect your wires. I've got this unplugged, so I'm not too worried about that right now. But I'm going to come on over and get my reading off my motor. and it's going to tell me how much resistance my motor has, which isn't really a whole lot. So we're sitting around 2 ohms of resistance. But the other thing that I can do is I can leave one of my wires connected to my electrical and then come on over and touch my frame and see, am I actually getting a reading? And if I got a reading while touching my frame, that's going to tell me I have a short to ground. But I have an OFL, which tells me that I do not have electricity going to the frame or ground. So it tells me I do not have a short to ground. So you can use that as a test. And again, if you have a short to ground on a component, a couple things you could be looking at. One, it could be shocking people when they touch the machine. Mike knows about that. He just ran a call on that not too long ago. Every time somebody grabbed the door, machine shocked them.
That was the other day.
Yeah. What's that?
The other day, yeah, I had a heater coil for the door was shorted out. So, yeah.
All right. Another thing could be not only getting shocked, but it could be tripping the breaker. So as the power goes on over to the breaker, could be tripping on out. And you test your equipment, and that you end up finding that you've got a short to ground. All right. Next thing that we're going to do is take a look at voltage. Like I said, this is probably the one that most people know how to use their meter for, but we're just going to go through it here really quick. Again, voltage is going to be your power supply. You want to make sure that you've got the proper voltage. It needs to be within plus or minus 10%. Basically, it's going to be based off of what your motor or your equipment calls for. So look at the data plate. You might see that it varies across the country. You might see people talk about 120. I've heard 125. I've heard 115. I've heard 110. So where is it exactly at? Well, we're going to base it off of whatever the data plate of your equipment states. If it says 115, it's plus or minus 10% off that 115. And that's where you want to be. Now, if you're outside that 10%, does not mean that it's not going to work. But what it means, it's going to work harder. And it's probably going to shorten its lifespan. So you want to make sure that you're at that proper voltage. And if you're not at the proper voltage at the outlet, you're probably going to want to let that customer know, and they can have an electrician come in and take a look at it and get that fixed. All right, other things that we have, well, you would want to check your source first, right? You want to check your wall outlet. Make sure you've got power there. If you don't have power at the wall outlet, what do you think would normally be your problem?
Strip breaker.
There you go. Could be a breaker off, right? So you may want to go turn your breaker back on. It could be that simple. Somehow the breaker tripped. Maybe something else is plugged into that same outlet. Or it might be 2 or 3 outlets plugged into the same breaker, and something else tripped that breaker. So you turn your breaker back on, and then you can go ahead and you can test your equipment out. As long as your equipment tests out, it doesn't have high amperage, it doesn't have a short to ground, it should not be what's tripping that breaker. Now, you could find out that, hey, maybe it's too much amperage and it's tripping the breaker. That's something we'll talk about here in a little bit, but it could be that problem. So we're going to want to go ahead and check your source voltage first. Make sure you got power, make sure you've got the right power. From that point, we can check our loads. Go into each individual component, motor, solenoid, board, whatever you're looking at, make sure that they have got the proper voltage being supplied to them. And again, make sure that it is not outside that 10% because that could be causing some damage. So let's take a look at, well, actually, let's go back to our PowerPoint because I'm going to show you this really quick. That's just a little diagram of what our electrical or testing our wall outlet should look like. So basically you're going to have a hot leg, you're going to have a neutral leg, and you're going to have a ground. Now, if you look at the hot and the neutral, notice that the bars that the plug plugs into are a little bit different in size. The hot leg is actually the smaller connection. The neutral is the larger connection. A lot of people think it's backwards. Oh, hot has to be bigger than what neutral is. Well, it's actually designed that way so you don't plug it in incorrectly. The neutral can't go into the hot leg. Now, you'll have some that your plugs might be the exact same size, the two-prong plugs, and you can reverse them. It's really not going to cause an issue in most cases if they're reversed, but in some cases, what you're going to find is it has to be connected hot to hot, neutral to neutral, because the hot leg is going to all your switches, and that's the way the hot leg runs. It should go through all of your switches, and you're breaking the hot leg, not breaking the neutral, and that's for a safety reason. But you'll also find that if it went to maybe like a timer board that wouldn't turn the component on for a couple of minutes, and you had neutral running to it rather than hot, it would never activate the timing board. So that's where having the hot and the neutral in the right spots really makes a difference. We had a Burger King that we had where we replaced the equipment. It had a timer board on it to keep the compressor from cycling. And they had the hot and the neutral backwards, and it never turned the unit on because the board never received power to the timer. So it does make a difference out there. So you want to make sure that you have got hot to hot, neutral to neutral, and then you've got your ground on the rounded section. So when you're doing your testing, you want to test hot to neutral first to make sure you've got a complete circuit, which should be giving you approximately 120 volts according to what you get in your area. Then you're going to go hot to ground. Hot to ground should give you the exact same reading as hot to neutral. The only difference is it's not a complete circuit because we have to have neutral return for a complete circuit. But what this is telling us is we do have a hot wire being fed to it. So maybe we did a hot to neutral test and we didn't get a reading. We can do a hot to ground. If we do get a reading, then we know we've got a hot leg. We just don't have a neutral return connected somewhere, right? And now we need to have an electrician take a look at that outlet for us. And that should, again, give us about the same as what our hot to neutral was. And the last test that I always use, especially if you're having computer board problems, and that is going to be a neutral to ground. And a neutral to ground test should come back with some voltage. There's always a little bleed through voltage that takes place, but it needs to be less than 3 volts. If you have 3 volts or higher between neutral and ground, that's what's called a dirty outlet. And what's going to happen is it's going to end up causing problems of blowing out your computer boards and a lot of other electronic devices. Mike knows all about that because he had an electrical lightning strike on his house that blew almost every component out that he had and left his wiring with, I want to say it was like 11 volts between neutral and ground.
That was a fun time.
Wow.
No, anything plugged in was fried from that lightning strike.
Oh, wow.
I remember Mike called me back up and he's like, why would it? I took a radio that wasn't even plugged in during the lightning strike and I hooked it up and it ran for a couple minutes and then it just burned out. And that's what it was. It had a dirty electrical and it was burning out anything that got plugged in until the electricians came out and repaired his wiring to the house.
Wow.
So if you're having problems with electricity, mainly computer boards, may not burn the computer board out. I've seen it where it just causes the computer board not to react properly. Or maybe it does burn the board out. Either way, test that neutral to ground. Make sure it is less than 3. If it is 3 or higher, then you need to have an electrician come out and take a look at it. And it may not even be the outlet. It may be the wiring in the wall, and the wiring is bleeding through the insulation, then causing that feedback. But the electricians can go ahead and get that taken care of for you. So those are just some of the readings that we are going to go ahead and look at. So let's go ahead and do a picture-in-picture over here. We're going to do a voltage test, and this is going to be AC. So when we're looking at our meter, where do we want to set our dial to do a AC voltage test?
To the wavy line with the V underneath it.
There we go. V and wavy line. So we will come on down. I got to look around here and make sure that I'm actually in the right spot. V and wavy line. And then we're going to go ahead and take our outlet, stick our meter in here, stick our probes in here, and we're going to see, are we getting our 120 volts right at approximately 120, right? Again, plus or minus 10%. So it could be 120, that would be what? 132 to 108. So as long as we're in that range, we should be good to go. Now, I always tell everybody you may have to go fishing because you stick your probes into the outlet and sometimes the outlet is loose. So what you're going to do is you're going to move it back and forth and you're going to be fishing in here until you get a bite and get a reading. So sometimes it's not as easy as just sticking it on into the outlet, especially with older buildings. You may have to move it around a little bit. All right, so that's our hot to neutral. We're getting 120. Now we're going to go to our hot to ground. And we've got our approximate 120. And then the last thing that we're going to do is come on into our ground to neutral. And we are getting 0.3. So definitely much less than 3 volts. But you notice we do have a voltage reading. Very, very small, but there is a little bit of bleed through there. And that is normal. A lot of people think you should have nothing coming through neutral to ground, and you will have a little bleed through every location that you go to. As long as it's less than 3, you are good. All right.
And is that happening in the path of the wire? Those electrons are just getting transferred from the hot to the neutral?
Yeah, basically it's bleed through the insulation on the wires.
That's
So
wild.
the wires are, touching each other tightly, they're wrapped together, and it's just a little bit of bleed through that insulation. But if you got some really old wiring, you could have a lot of bleed through, and that might be causing some problems.
Yeah.
That's really interesting.
AC current's basically magnetism.
Mm-hmm.
And those electrons are just magnetically carrying over.
Over.
Yeah, you
Yeah.
got to think, like Mike's saying, it's just passing through. It doesn't have to touch. Same
Yeah.
thing like when you're dealing with a transformer and you're stepping it down from 120 volts to 24 volts. Those wires never touch. The 24 volt side and the 120 volt side never touch each other. It is just magnetism that causes that. So same thing. If we don't have enough insulation on the wiring, that insulation could allow bleed through and that magnetism passing through, and now it's allowing voltage to go through those wires.
Mhm.
Which is sort of really strange because I just heard the other day Japan was working on voltage without wiring.
Mm.
Like a Tesla coil?
They're saying that they can control components in like an entire building without wiring. And it's like, I don't know if I want to be in the building.
Yeah.
Yeah, how does that prevent from like flowing to you? I don't understand how that works.
Yeah.
But we're talking about the little microvolts that are being transmitted through your cell phone that could cause problems.
Yeah.
What happens when you have 120 volts flowing through the air?
Just, yeah, all around you. That's wild.
That is crazy, isn't it?
Mhm.
Right.
Yeah,
All
I
right.
feel like the main thing with the phones is the radiation, I guess, from it trying to pick up signals. Does voltage do kind of the same thing where there's any sort of radiation coming off of it that would damage you? Hypothetically, if it was just going through the air, like that's kind of crazy to think.
Yeah, I really don't know, but you would almost think, wouldn't you? I mean, because everything
Yeah.
else would be based off that same principle that there is radiation attached to it. So,
Yeah.
yeah, I don't know how that would work, but it is a little scary.
Yeah.
Yeah, when you think it could be all around you.
All right, so we're going to move on into our amp draw. So with our amp setting, we're going to be able to read that actual flow of electricity, the flow of electrons, right? So basically you have all these electrons flowing down that copper wire going on over to your loads, your motors, your solenoids. And basically as those are flowing, that electricity is flowing, we can get a reading, and that's going to tell us, is our motor operating properly? And again, you want to have your amperage approximately within 10% of what its data plate requirement states. From there, low measurement is going to be telling you that you have less than a full load. So maybe you have a carbonator motor and you're testing it, but you didn't hook the pump up, or the pump is hooked up, but there's no water in it. So there's no pressure and resistance in that pump. It might be showing you lower amp draw reading than when you actually have the pump hooked up with water building pressure. So the data plate on the motor is actually saying this is what it should be under a full load. If it's not under a full load, it's probably going to show you a lot less. So just be aware of that. It may be giving you a little bit different reading because you don't have the proper load on it. I've even seen it with refrigeration. If it's trying to draw that temperature down and it's extremely hot, you're going to see that it's a higher amp draw. And then as it gets closer to its normal range, the amp draw drops down. Or we've seen if you don't have the proper refrigeration charge inside of a refrigeration system, it could be giving you a lower amp draw because it's not building the right pressure that it was actually designed for. So that could be showing you that you have a low resistance. A high measurement, a high amp draw reading, a lot of times that's going to be telling you things like you may have low voltage. So if you go and check your voltage, you might see, hey, I'm supposed to have 120, but I've only got 105 volts. But my amp draw is really high. Well, because of that low voltage, it's actually causing that motor to work harder. Other things that you have is that as it's working harder, could be a problem with the load. Could be that you have a larger load, like we said with the refrigeration system, trying to draw that temperature down. Could be damaged windings. If everything seems to be proper, you may want to have to get a resistance reading on it. You could have damaged windings inside there. I've seen that a lot with condenser fan motors where they've ran hot. It still runs, but it's struggling to run. And if you were to go ahead and get an amp draw, you're seeing it's a very high amp draw. And it's also, when you feel the body of that motor, it's very hot. The higher the amp draw, the higher the heat you're going to have. And that could be a problem that you run on into. So getting a amp draw measurement is really going to tell you, is it working properly or not? High amp draw telling you it's struggling, it's working too hard. Take a look and see why. Do you have the proper electricity? Do you have the proper loads? If not, or if everything is right, you're probably going to want to go ahead and change that component. You can also have what's called a locked rotor amperage. Basically, it's locked, maybe a fan motor or a carbonator pump or carbonator motor is not turning. It's completely seized. That's going to draw an extremely high amp draw. Could be a compressor on a refrigeration system as well. That normally is going to draw a amp draw about 3 to 5 times higher than what you would normally have. So if your data plate says that it's 5 and you have an amp draw of 15 to 20 or maybe all the way up to 25, that is going to be your locked rotor amps. Sometimes it'll say it on the data plate and give you the locked rotor amps. Sometimes it doesn't, but again, rule of thumb, 3 to 5 times higher is approximately your locked rotor. All right, any questions on your amp draw? If
Pretty
not,
clear.
I'm going to show you the quick amp draw here. Throw my motor on up. Maybe. Plug it back on in. I stepped on the cord here. But we have got our motor. We'll go ahead and plug it in. So I've got my motor and it's currently running. And then if I were to take my meter and I would take my amp clamp and I wrap it around one wire. It does not matter if it is the black hot wire or if it is my white neutral wire. I just want to wrap it around one wire. And I also want to go ahead and set my meter to amps AC. And then from that point, I wrap it around a wire and I get my reading. Let's see if you guys can, there we go. So we're about 4.3. Now you can do the neutral wire. Just remember, whatever goes in has to come back out, right? So come on over, looking at it, jumped up about 4.3. So it's giving you a reading as well. So you don't have to get the hot wire. Some people are all, I can't get my meter to go around the black hot wire, but you might have the ability to go around your neutral wire. It can go around either one. It does not matter. So you can go either one. The key is you only wrap it around one wire at a time, because we were sitting at about 4.3, whether we were on the neutral or the hot. But if I came around here and I wrapped it around the neutral and the hot, now we're at what? 0.04, 0.03. Basically, what's going in and then what's coming out is canceling each other out. and we're not getting a reading at all. And that's why you have to get a reading around one individual single wire. Same thing with the whole power cord. You can't just wrap it around the power cord and get a reading, because you have both the hot and the neutral in there and they will cancel each other out. So it has to be around one single wire. And if you're dealing with multiple hot wires within a piece of equipment, I found that if you went around multiple hot wires, it might double it. If you had 2 wires, 3 wires would triple your reading. So again, 1 wire at a time when you get your reading. Now, another thing that you might run into, well, I'm sorry, we'll talk about that here in a little bit, but you might not be able to get in here, and I'll show you how to be able to get in there and get a reading if you have to. All right, any questions on our amp draw?
Yeah, I did. So with the amp draw on that sticker that is on that motor, is that going to tell you how many amps you're looking for to put you, because you need a number to know within range, right? And so I
Exactly.
think you had like
And
3
on
point
this
something
one,
there.
let me go ahead, see if we can zoom on in. There we go. So down here, it is telling me my horsepower, my RPM, and then it is also telling me my full load amps.
Okay.
8.4 to 6.
6.4 to 6.3.
I'm sorry, 6.4 to 6.3, or 3.0 to 3.1. And the reason this is giving me multiples here is because this motor actually is a dual voltage motor. It could be wired as a 120 volt or a 220 volt motor. So basically it's saying if it's 120 volt, we should be looking at 6.4 to 6.3. If I've got it wired as a 220, we should be looking at about 3.0 to 3.1.
Makes
Okay.
sense.
Yeah.
For sure.
What does that SFA, is that safe something amps or
Service factor. Oh, SFA.
so, yeah,
Yeah,
because it
that's
has
actually
that same range, but
yeah.
it's just labeled differently.
Yeah, they've got it. Well, I think it might actually be also because this is designed to be a 60. If you look down here,
60 or 50
No,
hertz.
60 or
60 to
50
50
hertz.
hertz. So this is something the US uses 60 hertz. How many electrical cycles per second is taking place? Remember how I was saying that alternating current goes both forward and backwards, right? So how many of those cycles are taking place 60 times a second? Or 50, which is pretty much everybody else. So the US has always got to be a little bit different. But Europe and I think South America and I think Canada even runs on 50. So we want to have it at 60 hertz. So you'll see most of your equipment is labeled 60. This one has the ability to run either. It can do 60 or 50. And that's probably why you're seeing a difference in your amp draw, telling you one is 60, one is 50. But in this case, it doesn't matter. It's going to be the same thing.
Yeah.
I had to
Okay.
look that up. Service factor amps. That's
Oh,
the
service
maximum.
factor.
Yeah, the maximum current an electric motor draws when operating at its full service factor. That's pretty much the same as the FLA, so full load.
Yeah, just its full load.
Mhm.
Well, actually, I take it back with the 5060 because the 5060 is down even lower. If you look at the very bottom of the screen, you'll see the 50 hertz readings, which is a little
Oh,
different
yeah,
than what
there it
this.
is.
Mhm.
Yeah.
And then I thought this one actually said it's voltage, but I'm not seeing the voltage in here on this one. Might be somewhere else on the sticker, but it's not on this
Volts.
sticker right here.
Volts
Right there.
Yeah,
Volts.
120.
yeah,
Yeah.
Do you see
Right
it?
there.
it's, yeah, I see it up on the left.
Right below RPM, above hertz.
Oh, there we go. Okay. I'm looking at it upside down and backwards on my screen. So, but
Yeah,
I
go
can't
see
even
that eye
point at it
doctor
because it's
next week.
backwards. What'd you say? That's normal?
No, I say go see that eye doctor next week.
Oh, I do have to see the eye doctor. Yeah. Well, would think what we do upside down and backwards would be normal because you're underneath the counter. You're upside down and backwards working on stuff. But
Right.
Yeah,
there's our voltage, and given our voltage and our voltage range.
yeah.
But All this is going to tell you, the data plate tells you what to look for. It does tell you your voltage, does tell you your amperage. Unfortunately, what it does not tell you is your resistance. And that's like I tell everybody when you're doing it, when I do resistance, I always look do I have a 0 telling me I have a direct short? Do I have OFL telling me I have a broken winding? If not, then what is my reading? And compare it with a good motor or a good solenoid or whatever that part is. All right. Jump on over here. I always like to show this. One of the things I always tell everybody is when you think about voltage and amperage, they're sort of like on a teeter-totter. And voltage goes down, amperage goes up, voltage goes up, amperage goes down. They're sort of related to each other. So if your amperage isn't correct, I always go back and take a look at, do I have the proper voltage? That could be one of your big problems with your amp draw. And your amp draw is really going to be telling you, okay, your motor doesn't seem to be working properly. And again, take a look at your voltage first. If your voltage is good, take a look at your load. Make sure that your load is good. It's operating properly. It's not hung up. It's not locked. It's not working too hard for some reason. Maybe you've got the wrong pressures and the pressures are causing issues. If all that is correct, then now you're looking at, okay, now I've got a motor that needs to be replaced.
Mm-hmm.
All right, now we talked about what if I can't get to my wires and go ahead and test my wires out because my wires are so close to the connections I can't actually get that clamp to go in there. That is where the line splitter will come into place. You can buy these for under 20 bucks at most hardware stores. You can get them at Amazon or whatever. But the line splitter comes in very handy because what it's going to allow you to do is get both an amp draw reading and a voltage reading. So what you can do is take your meter's amp clamp and clamp it into one of the holes. You're going to find out that there's two holes, one that's marked ×1 and one that's marked ×10. If you're using a electrical or a digital meter, you're always going to use the ×1 hole. The ×10 hole is if you're using a very old analog gauge that just has a needle on it. Sometimes the reading was so low you couldn't read it, so they boosted up by 10 so you can get a better reading off of it. But with the digital, always go to the ×1 hole. From that point, you just plug the splitter into the wall, and then you plug your component into the other end of the splitter, and then go ahead and get your reading. And that way you don't have to separate it because the hot leg is running down one side, the neutral leg is running down the other side, and then from there you can go ahead and get your readings. Makes it nice and easy to get an amp draw off of a piece of equipment. You also have the ability to do a voltage test. So it will have little holes. Most of them are designed this way, and they'll have holes. So if you're trying to fish around an old electrical outlet and you really can't get a good connection on that, you can always plug your splitter into the wall. Just simply take your meter, plug it into the two holes that says voltage test, and then set your meter to voltage, and you'll be able to read the hot and the neutral wire. So that comes in nice and handy if you've got an old outlet that's giving you a hard time getting a reading in there. So basically, here's a picture of what that would be like. So we will come back on over, get rid of this motor, get it out of the way.
Just to clarify, so that AC splitter tool that you just showed us, that's essentially doing the exact same thing as you showed us on the carbonator or on that motor when it was live, how you singled out that line, but that's just on the other side of that wire essentially, and you're testing it near the outlet rather than
you're just going to test it wherever it plugs in. So here is the plug for my motor. And all I would do is I would take and plug it in. If I wanted to test my motor, you can do an entire machine, or you can do it by each component if it has its own plug. But you would just go ahead and plug it into the splitter. You're going to take your meter. You'd have it on AC amps. And then you're going to look at this, and there'll be a ×1 hole and a ×10 hole. So we'd want to use the ×1 hole. And we're just going to go ahead and put it on in there. Then from that point, all we need to do is plug it into an electrical outlet. And then you can go ahead and get your reading. Remember, we were at what, about 4.2, 4.3? And we're at the same reading right here on our line splitter. And we didn't have to go ahead and search deep inside the machine and find a way to get this clamp around that wire. The other test that you can do, like we said, is we can go ahead and set it to voltage. And we come on over, and there are voltage holes right here that I can just go ahead. Well, this meter may not, or these prongs may not go in here. Yeah, they did.
Yeah, with more of these outlets getting childproof, you can't really get your prongs in the outlet to get a good contact with the metal in there. So I use a lot of the splitters for just checking voltage
Yeah.
of the outlet.
Mm-hmm.
So hopefully you guys can see that, but it's showing me that I've got 120, 121 volts, and it's just going to that line splitter.
Mm-hmm.
I use the splitter a lot. I don't know if anybody's ever used the splitter. I know Mike uses the splitter.
Yeah, I use
No,
a
I've
splitter. It's a good
I've never
tool.
used one before.
All right. Yeah, the line splitter, I like it, especially when I'm doing refrigeration. A lot of times I'll just go ahead and I'll put the line splitter right on the main cord for the machine. That way I can get an amp draw off the entire machine, making sure that I'm not drawing too high of an amp draw that could be causing it to trip the breaker out. And then I get my amp draw reading right off the bat. Um, but that's actually a really good test. Another thing that I like to do as a first test when working on a piece of equipment is I might come on in and set my machine to ohms. And then like we were saying about how going to the electrical connection on a motor and then to the frame, I'll do the same thing where I'll come on over and I'll test. Let me see if I can put this up. I don't know if I've got a picture on this or not. But what I'll do is I'll come on and I will test the entire machine by first off coming on over and going one my electrical connections and my ground and make sure that I do not have anything, which I should get in OFL. Can't see if that was actually reading that way or not, but can anybody see that? Are you guys getting an OFL on that?
Yeah, we saw it.
Yes.
Yeah, that was an
Clear.
OFL reading. So I just come on in, I go electrical to ground, make sure I got OFL at my plug, and then I want to make sure my ground is working. So I'll go ground, and then I'll come on over and I'll go to my frame. If I go ground to frame, now I should be getting a reading in between there. So that tells me that my ground wire is coming all the way down my cord, all the way to the frame, grounding my frame out to my component or my machine. And then you do your electrical to ground to make sure it doesn't have a direct short. This works out great if you've got one that as soon as you turn it on or plug it in, it kicks the breaker. You can go ahead and do this test to see if it's actually something wrong with some direct to short. Then you have to trace it down and figure out, okay, which electrical wire is grounded out to the frame. But at least this tells you, yes, it is grounded out to the frame. You need to go ahead and make sure. Or maybe somebody's getting shocked and it's because you don't have a good ground wire. So we test it from the ground at the plug to the actual frame and make sure it's grounded out and it's getting a good reading. All right, so that is basically our electrical class. Do we have any questions before we basically wrap this on up?
I did have
No.
one clarifying question. When we were talking about the plugs and how some of them have that reverse plugs, and you brought up that Burger King that had the timer issue going on. With
Yeah.
plugs like that, are they typically like labeled like hot and neutral on there to where you would be able to easily know, or is that kind of just plug it in, you have to wait 10 minutes if the timer doesn't turn on, then swap it around, and then you'll kind of know that?
Well,
Because I
inside
mean,
the
obviously
machine, it
on the
should be hot and neutral. Hot normally is going to be a black wire. Neutral is normally going to be white coming on into the machine. It may have different colors, especially if it's like a 220 volt machine. You'll find that you'll have some different colors there as well. But normally something is going to be labeled to let you know which one is hot, which one is neutral. Um, we definitely had that listed on ours when you were looking at the wiring diagram to know exactly which one was which when it was going through there. So we knew how to figure that on out. The problem that we had, like we said, is we weren't getting power to that timer board. So then we came back on over to our outlet. And as we came back on over to the outlet, what we ended up finding is that when we did our hot to ground, we didn't get a reading. But when we had very little volts. When we did our neutral to ground, we had 120 volts. So it was really weird. Hot to neutral was 120, hot to ground was almost nothing, neutral to ground was 120 volts, and basically all that was telling us is the neutral and the hot wire were reversed in there. So
Hmm.
that's an easy way to test it out. Just remember, the hot is the smaller connection, neutral is the larger connection. So you
yeah,
should have 120 between neutral hot, 120 between hot and ground, but then you should have less than 3 volts between neutral and ground. And if it's giving you
yeah,
that in reverse, we've got 120 between neutral ground and almost nothing between hot and ground. You know your hot and neutral are backwards.
yeah, yeah. I guess my main question was like on the plug itself, where you're plugging it into the wall, because you know how you said some of them it could be either up and down this way, or you can plug it in this way. Is there a way to know on that plug itself which one's supposed to be hot and which one's supposed to be neutral? Because in a situation like that, I mean, it's obvious you can see the size difference on the outlet, but on the plug itself,
Yeah.
is there typically a labeling on there, or is it kind of just guess, am I putting it in this way? Or am I putting it in this way?
Right.
If
Well,
it
with
doesn't
this
have
plug,
that ground.
you'll notice that the hot and neutral are the exact same size, but because of the orientation with the ground wire, you can't plug it in backwards. It will
Okay.
always be
So,
correct. Now, if you had
okay,
one
because I've
that didn't
seen
have the
like,
ground and you
yeah.
only had a two wire,
Hmm.
the two wire, the neutral should be larger on the cord. I don't think I have anything with a two wire plug in here.
Yeah, and I don't think most components would have a two wire. That's usually like lamps and things like that.
Yeah, yeah, but you'll
Okay,
find
okay.
in a two wire, it's going to have a larger connection on the neutral than what the hot. So again, you can't plug it in backwards. Now, I
Okay.
have
So for
found
instance, like
some,
like this one for my computer, like there's no components that we work on that are gonna have a plug like this one for my computer where they're both the exact same size. I can plug it in this way or I
yeah,
can plug it in this way and it's the same regardless. So does that
well,
make
the nice
sense?
thing is if you're dealing with a two wire plug and they're exactly the same, I'm going to say most of the time you're not going to have to worry about it
Okay.
because it's not a requirement of whether hot is inlet or outlet.
Gotcha. Okay. So
It's really
essentially,
not
like
going to
if
be
the
a
plug's
problem.
designed like this, you don't
Yeah.
gotta worry about it. But if
Well,
the
like
plug
a
does
lamp is
have
a
the
good
different
example.
size,
If you
you
were to
should.
reverse the neutral and the hot on a lamp, it's still going to work. The
Uh-huh.
only
Hmm.
difference is the switch on your lamp is going to kill the neutral leg, not the hot leg, but
Hmm.
everything will still function and you'll never know it. The only time you would ever
Gotcha.
know that something's wrong is if you're working on a two wire plug on something that you're trying to service and you turn the switch off and then you go and you work after the switch and you get shocked. It's because it turned the neutral off, it didn't turn the hot off,
Okay.
and it didn't have a return path. But when you grabbed a hold of the wire, you became the return path and allowed the electricity to flow. And that's why they want the hot on the. They basically hot should always go on over to your switches, and that's why they want it in the right order. But you'll find most of them, most machines will actually work whether it is correct or reversed. But
Okay. That's great to know. Thank you for that clarification.
all right,
Something maybe to
I
bring up in a future class is with direct current, DC voltage. Sometimes polarity makes a difference for that component to work right. So something maybe to add in on a future class.
Yeah, that is actually a good point, something that we want to add back in there because like we said, with AC, we could reverse hot and neutral and it really won't make a difference other than for safety factors. Or, like we said, if we had like a timer or something in there that absolutely had to have the hot wire going to it.
Hmm.
But more than likely, 99% of the time, you'd never even know it. But on DC, like Mike said, absolutely a requirement to have the DC hot and the DC negative wired correctly. Because if not, it's going to do one of two things. It's going to cause your equipment to run backwards. So you might have a fan motor or a solenoid or whatever, and it's actually operating in the reverse order than what it should be, or it won't work at all and you're thinking it's a bad component, and all it is it's backwards. Reverse the two leads. I've even seen it
Hmm.
where it was labeled correctly on a DC component. It is labeled hot and negative, and it was hooked up the way it was labeled, and it didn't work. And we reversed it, and it worked because even though the wires were labeled correctly, where it was connected someplace else in the machine was backwards.
Mm.
Right.
Okay. That, yeah.
I had an odd one a few days ago on I had a carbonator that wasn't getting power, and I went down the areas in the small little closet only had one power outlet. So I went down, tested the power outlet. I had no power. I go to the breaker breaker panels and in the back room, and the breaker. I'm checking the breakers. I was able to identify the breakers, and the breakers were good. They weren't tripped or anything, but I still had no power to the outlet in that closet. And then so I went to look for a another power outlet that was nearby, and I found that one right outside on the wall. That one didn't have power either. But then luckily I found out that that particular store had had a water main break in the building. So water was in all of the walls and everything. So what we ended up figuring out was that those outlets had gotten damaged from the water main break, and they had to have an electrician come in to replace the outlets and stuff. But at first, it was throwing me a little bit because I was expecting the breaker to be tripped uh,
Yeah.
from shorting out or something, but they
Another
were
thing
good.
that it could be, and I've experienced that at my house with you're dealing with a water issue, those two outlets might be connected possibly with even another outlet.
Mm,
And one of the other outlets is a GFCI, like you find in
mm.
your breakers or your kitchens with a little resettable button on it.
Yeah,
And
yeah.
if that GFCI trips, it shuts the power down to every outlet that's on the circuit, but it doesn't always trip the breaker. So you're looking at it going, okay, my breaker's on. I should have power, but I don't have any power to these outlets. And it was throwing me because it was my front and my back door outlets outside, and neither one of them had a GFCI on it, but they tied into an outlet in my basement that did have a GFCI. But when we had a heavy rain, the water got into the outlet on the outside unit, caused the GFCI in the basement to trip and shut the power off to everything. So if your breaker's on, you may want to look around and see, can you find another outlet that's off that is a GFCI and can you reset it? But on the other hand,
Right.
like you're saying, with them having water damage in the wall, it may have actually shorted the whole thing out. It may even have taken the breaker out with it without it even tripping. So it still looks like it's in the on position, but it's burnt out. But that's where your electrician has to come in and look at it.
Yeah, yeah, definitely. That's a good idea though, checking for the GFCIs on somewhere in there. 'Cause that is possible. I've seen that before.
All right. Any
Well,
other questions or any thoughts or
I mean, yeah, I've got thought one. I just want to say thank you. That was a phenomenal
Yeah,
class. That was really
awesome.
great. Your production value, everything, it's so great. on point there. Some food for thought that I was had just during the classes, definitely like items. Because I was sitting here playing with batteries and things like that, but being able to work along with you, I think would be really valuable. So like like we were talking, used parts, solenoids, things like that. But even just for this basic multimeter, having like little light bulbs you can test, and different things like that, I think would be really cool. And then my brain just went off with other classes because like I had one, not a question. Well, I do have a question, but it's probably a much longer class. Why do switches fail? Like what happens inside a switch for it to create that resistance so much that it starts heating up and things like that?
Well, a quick answer with that, you got to think that the switch is making and breaking contact. It's got points in there. So
Hmm.
basically, you've got the points coming together, the points separating. As they're doing that, there's going to be a little arc that takes place.
Okay.
That arcing after a period of time is going to leave a residue there, a carbon buildup,
Hmm.
and that carbon buildup is going to cause resistance. Once you get enough carbon buildup, and also that spark can cause a little damage to the points, and those points
Hmm.
can start to pit. So as it's doing that, it's damaging the point, it's leaving that carbon buildup, it's causing that resistance. And that's why I was saying when you start to see a high resistance in that switch, you know that it's taking damage. You might as well, if you've got a switch on, you go ahead and replace it before the whole system eventually goes down. But you can actually see that as you're servicing it and then prevent that customer from having a down point by just go ahead and replacing that component at that time.
Hmm. So it's like kind of just welding itself over and over
Yeah,
inside there.
yeah, it doesn't always weld itself shut, but it can damage those points to the point that they're not transferring the electricity very well. It's causing a high amount of
Gotcha.
resistance because of that damage.
Got it. Okay. Thank you. I
Yeah,
mean, yeah, other than that, I mean, you covered so much great stuff just from the basics, but then into electrical theory for AC and DC, your knowledge checks, that
great.
was really cool. Engaging there. And yeah, I mean, I took away some knowledge that I had no idea. And I had a story. I worked at, you guys probably remember PC Richards on the East Coast. It was like a appliance store. It was mostly in like New York and stuff like that. I was like 17 working. My uncle was a master electrician for the union. Up in holding the rafters, cut in with my lineman pliers into a 120 line that I thought was off, and
Mm,
my hand just clamped up
mm.
on top of like a 10-foot ladder in the
Wow.
ceiling.
Oh,
Hair went everywhere.
oh, jeez.
But they had to pull me off the ladder because I couldn't break that
Wow.
resistance. It wasn't powerful enough.
Wow.
It just cramped my hand to the I-beam in the ceiling. And yeah, so
Mm.
Yeah,
safety.
that's the danger of 120 volts too. Like we were saying, there's not enough
Hmm.
force to push you away.
Yeah, yep. And I was just on the ladder and shaking a little bit, and they were able to pull me down and catch me. But
Yeah,
safety, I
just
love that you
holding.
had safety electricity in there. Yeah, very good class. Thank you very much.
And you're making some points of what I want to add to it because Mike talked about a few things. You're talking about something. When I'm talking about safety, I think another thing I might want to add, because I used to say this in my longer classes, and that is if you turn the switch off, how do you know it actually turned the power off? Break out the
Mm,
meter and check it before you work on it.
Mm.
Hmm.
mm. Yeah,
Mm.
very true. That meter is our savior, really.
Yeah. Yeah, you might turn the
Yeah.
switch off and use the meter and then find out the switch is broken and didn't turn the power off. Well,
Yeah,
good
Hmm.
test before you grab a hold of it, and now you're getting electrocuted off of it.
Right.
right.
So when this might be a dumb question, but I just need to wrap my brain around it. When you say quick test of that switch, when you're testing the switch, do you have to take the wires off of the back end of the switch and test only the switch itself? Or like how would you safely test for that? Like test for no power on the switch, or are you like where I guess yeah, where are you doing that? How would you
Probably
do that?
the safest way to do it, like we did with the ohms test, disconnect power completely, right? Unplug the machine or shut the breaker
Yep.
off. Then go ahead and disconnect the lines and ohm the switch out. But if you're a little worried about that, you want to go even a step further. What you could do is um, you could, while it's wired up, take your meter in voltage and say this is your inline side, right? You got power coming in here. You just
Uh-huh.
take your meter and read here, and then take your other lead and go to ground.
Mm.
And
Yes.
then that should
Okay.
tell you you've got
Yes.
120 volts. Then come to the outlet side. If it's on the on position, you should still have 120 volts, but in the off position, you should have zero. And if you're still getting 120 volts in the off position, then you know power's coming through the inlet, through the switch to the outlet, still flowing through, even though it's off.
Okay. Thank you for that. That makes a lot more sense now.
Yeah, so you can
Appreciate
do
it.
it voltage test, you can do it ohms test, whichever one you want to do, but that'll actually show you how whether that switch is turning off or on properly.
Good point.
Yeah. Thank you. Like I said, this is awesome. I can't wait to see where this goes and what trainings you guys can produce and how we can get technicians in here because I think the amount of knowledge you guys have and the way you present is just it's beautiful. It's a great job.
Yeah, like we
It
said,
is
this is
really good.
just like a fundamental, so we could do quite a bit more and even get
Oh
down
yeah.
into the specifics like a valve, a regulator, a carbonator, you know,
Hmm.
things like that.
Yeah, some advanced
And
work.
then this is just your basic multimeter, and I tried to type in or put in a little bit of theory and application.
Hmm.
But then I've also got another one that I would like to do with this where it's going to be much more application and we take it into a more advanced step with the electrical process. And then the same thing with refrigeration. We can do a refrigeration talking about how to test out a compressor, how to test out different components, the start relay, the overload, the capacitors, things like that, and go ahead and do that. Pretty much everything you would need without having a refrigeration license and tapping into the system.
Yeah, that's a real good idea. Because you know, a lot of techs that may not have that certification, that'll be very helpful to them to be able to hit some of those test points that would allow them to be able to tell if it's a actual refrigeration issue, and then they'll have to get a refrigeration tech in there. Sometimes you run into that where or it could have been something that maybe they could have figured out and changed the part um, and get the equipment fixed. But that's a real good point. 'Cause, and then like with Patrick when he's talking about the switches, and you mentioned about the carbon buildup that the points get and the contacts get. That's another real good one there because even on the refrigeration side, they could take a look at their failed start relay, uh, even and you can open that relay up and you can see the pitting and you can see the carbon buildup on them. So that those are some real good topics that you could touch on.
Yeah,
That'll be very good.
absolutely. You
Yeah,
know,
we did a
I ran a service call yesterday that was like so simple. And that's the refrigeration. I like to go in the whole process of how refrigeration works. And again, you don't have to have a license, but it does give you an idea to how it operates, how to diagnose it, and how to prevent it going on over to a refrigeration company that really doesn't need to be called to go out there. Save the
Hmm.
customer a ton of money, that really is just a waste because it was a simple thing like maybe temperature control was bad. It just needed to be replaced.
Mm.
But I
Yeah,
ran one yesterday that was nothing more than the condenser coil had so much lint on it that it wouldn't cool the compressor down and cool the
yeah,
refrigeration system down. I just had to
yeah,
clean that out and they were back up and running. But unfortunately, a lot of times something like that could be misdiagnosed because they don't understand how it works. And then now you've got a refrigeration company running the call.
yeah.
Hmm.
That's true. When all it needed was a simple coil cleaning,
Yeah. Yeah. Just
Hmm.
5, 10 minutes and you got the coil cleaned and you're good to go and you're done.
Yeah, then that's a chance to get them on a little maintenance plan.
Yeah, absolutely. We
Abs
are just
Yep.
talking about that.
Yeah.
Good
Alrighty.
stuff, man.
Well, yeah, gentlemen, thank you so much again. And if you can, whenever if this is record or done downloading,
y'all
because it
send it.
was about
I
2 hours. Just
it should be in the cloud. I think I'm in
okay,
the cloud,
cool.
but I'll send it your way.
Awesome. Thank you so
Nice.
much, guys.
All
Thank
right.
you.
Thank you.
Yeah,
Good job,
we'll
Damon.
be
Thanks,
in
everybody.
All right.
Mike and Damon. I'll reach out to you guys after I talk to Steve, and yeah, we'll figure something out.
Sounds great.